As my title is elementary approach. So how can we do it in the very elementary way? So let's see. I try a new approach way to see. First, what is the twin primes? We know that. But first, we try to formulate this problem to see what's going on. So first, I introduced one function. It is should be the characteristic function for the primes. So we say P is a prime. And we say rho of Pn is equal to the function only taking two values. So if n is a prime, otherwise it is 0. That's called, we know that, it's a characteristic function for the primes, right? And where the bigger domain is just the natural numbers from 1 to 3, so something like this. So then we say, let me ask one question. Do you think this function is simple? Should be simple, right? That is why we say some deeper problems in number theory are simple, because at least it's easy to understand the problem itself. But it's not simple because if we try to solve the problem, that's not simple. This function actually reflects the simple and the non-simple of number theory. So now let's see twin primes. Let's consider this one. The product of two row values. So this equals what? I'm not going to say something more. It's elementary. We can prove if both n and n plus 2 are primes. Otherwise, right? So now we say the twin prime problem is there are infinitely many pairs of the primes, the n plus 2, both are primes. So it is here, please allow me to use something a little more. We use a sigma, the summation, but it's still, I think it's still elementary, right? Oh, later. Capital N is a large number. In the case, it's approaching infinity. Right? Because in such a case, in this dimension less than or equal to capital N, there are many terms which is equal to 1. So n goes to infinity. That becomes there are infinitely many n such that this is equal to 1. So we just give this. We say, oh, it's easier. But how can we compute this sum? Here, it's not like the computer science. There are some special words. It's called the computable, right? Something. This is logically is not computable, such a problem. But we should be able to at least to get some bounds for such a sum. Precise the computer it, if you give me the precise value of capital N, even it is 10 70 million or something larger, still we are able to evaluate, in particular using computer science. But now n goes to infinity. At least it's not a simple problem to compute this sum equal to what. But our question could be, we may not be given the precise values, although there are certain more deeper conjectures on this sum. But we may find a lower bound. The lower bound, depending on the capital N goes to infinity, the lower bound goes to infinity. That's all. So even this question is question 1. Can we find we say, I just say to find I just mean say lower bound, but this should be efficiently. Namely, this should be some function, could be a complicated function depending on capital N. But one thing is, it must go to infinity. Otherwise, we still nothing. But until now, we are unable to do this. Because my result, it is a weaker form of the twin prime conjecture. I got the bound, there are infinitely many pairs of primes. The gap is less than 70 million, right? Right now, this 70 million is improved to 246. But still it's not 2. If it is 2, then that's all. So it is weaker. So now let's see. We are unable to do this directly because as a function, the rho of n, the definition is simple. But what follows is not simple because this is number theory, right? So people may ask some weaker form to see that. This is based on a very simple factor we learned from elementary schools. What means that? Usually the addition and the subtraction are easier than multiplication, right? So here, if we get two factors, take the product, currently we are unable to handle such a sum directly. But if we replace this one by something else, maybe something could be easier to handle. So now let's consider. Oh, sorry, I forgot one thing. The answer is unable to do this. Now, can we find some alternation or substitution of this one? That is, but this is not precise. I say others. We consider one sum like this. This equal to what? We know it is equal to 1 if both n and n plus 2 are primes. Then otherwise it is If 1 is a prime, so 1 minus 1. If both are non-prime, so is negative 1. So now the question, I'm not going to write down it, but I just say, can we find the infinitely m such that this one is strictly greater than 0? If we can do that, also we answer this question. Now it is tricky. Actually, this is the basic idea about the analytic number theory, or some the so-called sieve method or something is what? So that's our question 2. Sorry. Can we find something, some an which is greater than or equal to 0? It is a new sequence such that for n, because we just consider n is large, let's n start from capital N to 2n or 3n or n squared, that doesn't matter. Let's look at this meaning. If this here, everything is just real numbers, we don't worry about the complex numbers. So a sum is greater than 0 means at least one term is greater than 0, is positive, strictly positive, right? So the question is, if this is strictly positive, then this is the product of these two factors. This is non-negative, but if the product is positive, so let's see. Because we have this condition, and also this is also positive, can never be 0, can never be negative 1. And so and also we will take a large value of the n. Actually, the capital N always goes to infinity. So this one just means there is n greater than capital N such that also greater than capital N, still we have the pair of twin primes. So there are infinitely many twin primes. This is the idea. And this is maybe our words we say is computable. Maybe it's possible to do it better than that. The first one is we're unable to do this. But unfortunately, still right now, we are unable to deal with this one. Then but this one gives us a hint. So the motivation that at least we can do some weaker form of the twin primes. So let's see. Let me write down here. Oh my God, here. We cannot move this board. So sorry. I should have put it up earlier, but we know that. Sorry, still we are unable to do to do this. But let's consider one. Here, I apologize for something could be more technically a little more complicated. We have to use some parameters, something like these. So fixed. A sequence, and we say this is a the positive a 0, it is equal to 0, then less than a1, less than a2, less than ak. But it is fixed. We consider here we already use a and b and yeah. Oh, sorry, equal to this. Here we may not use this. So of course, this is maybe is a general form than that. If we just take a k equal to 1 and the a0 is 0, this is 2, then that's all. It is just this. Also, this function also tells us something like this. If n plus a1, we just say this one, that fn is greater than 0. Actually, that means it is greater than or equal to 2. Implies at least 2 of, sorry, not of, the sequence n plus a0, it is just n. And their gap between these numbers is less than or equal to ak. Ak is a fixed number, right? So at least if we can find the k, we can find the fixed a is just a tuple of the image. They are all positive integers. To prove for infinite n, this is greater than, is strictly positive. Then that is say there are infinitely many n such that for these numbers, at least 2 of these are primes. And the gap between these 2 is less than a fixed number. Say this number is equal to 70 million, not 100, right? This is ideal. Then also what I mentioned in the second part, in the second question, something about that works. So our question is, let me write down here. So question. Also, let's start. Here should be for any large n. Here, start from capital N, but here if it is 2n, 3n, 100n, that doesn't matter. I already used the f of n. This was what I had achieved 9 years ago. And actually, there are many sequences. I just say, but for these sequences, for these fixed tuple of numbers, there should be an admissible condition. I'm not going to say in detail. But anyway, I can find whenever this one is less than, is close to 70 million something. This is proof. First, I proved it. Now the next, how to choose the coefficients is a sub n. We only require one thing. They must be non-negative, right? Because some are negative, some are positive, then nothing, non-negative. But the next, more seriously, the question is, should we able to evaluate such a sum? Here, let me say something just in number theory. Usually, a lot of things in number theory, in particular in analytical number theory, are reduced to evaluate, to compute the certain sums. These certain sums, if we are given, that depending on capital N or something. Yeah, sorry, this room is a little warm. But that's okay. If the capital N is given, even capital N is equal to 1 million, 1 billion something, at least now the computer programs are very, very strong, very powerful. We can evaluate it, right? So if you give me a capital N, you give me the A0, A1, A something, we're always able to, but sorry. Sorry, this should be CB1. Sorry about that. I apologize for this. So we are able to do it, but theoretically, for every large capital N, even this, the A0, A1, AK, that could be given. That doesn't matter. How can we evaluate? So in analytical number theory, always we evaluate a sum. Sometimes it's called a arithmetic sum, involves functions like this. First is we should be able to find a main term. It is equal to m. So in analytical number theory, usually we can, the sigma, it is equal to m plus e. Here the capital M is called the so-called main term. Capital E is the arrow. Why we have this one? Because usually the arithmetic functions are so complicated. We're unable to, except for some few situations, unable to give the explicit answer, this equal to what? Always we need the arrow term. But now the question is, can we prove so I say we evaluated this sum, we find it is equal to m. M usually should be a positive value. So if it is equal to the main term, we forget about ignore the arrow term. That's all, it is positive. But we have to consider this. If we are unable to say usually the arrow term is so complicated, we can only give the upper bounds for this. We're unable to precisely to evaluate this term. So we should prove the upper bound for the arrow term, which should be less than the main term. Otherwise, our result is still doesn't make sense. This, like some experiments in the physics something, we try to measure maybe something like the mass of some article, then we get a value. But if we find that the error in the measure process could be larger than the measure, still that doesn't work, right? And also, I would like to mention, although I do know what's the measures of your maybe various measures, but sometimes the number theory, the behavior like the physics, something like this. So can we prove this? Now that is, but also we have a question, how to choose these the Bn, the coefficients. This is arbitrary, this is a given function. But this we have many choices because we only require this non-negative, right? How can we choose these? Like to find a needle under the ocean, right? So here, let me say some background from this. So this is the full background from the number theory. I don't know, but I can give the definition of a very fundamental arithmetic function in number theory. That is the Mobius function. That is mu n equal to, it is equal to 1 if n equal to 1. It is equal to -1 power, so it is positive -1 if n is a product of distinct primes, distinct primes. And these are not equal, not repeated. These are just primes. And the 0 otherwise. So we only need this one. And some basic relations is like this. Also here, it is a summation over the divisors of n. So also we just say equal to the sum over divisors of n, and we have some two basic relations. One is the second one, Mobius function, can be used to start the prime numbers because this is all. Here, the logarithm, usually we take the natural logarithm, but here it doesn't matter. Logarithm equal to Otherwise, like this. So this one just say the sum over the divisors of n. Oh, let me say, these things numerically, if you don't believe, you may try some value. Say n equal to 105, or here the n equal to whatever, 49, or you may try to see. It is these are always true. In particular, this could be a hint of applying certain sums divisor with the involving the Mobius function to study primes. Just use this. So using the Mobius function, so we say that our choice of Bn is like this. First, here still it is a trouble in just the modern civil theory. We need a sequence, at least it should be non-negative. But how can we guarantee this non-negative condition? It was a great mathematician whose name is Selbach. He find we just take Bn in a form, Bn equal to the square of Cn. Then we try to determine. Then the problem is reduced to choose how to find the Cn. Then the Mobius function involves a Cn equal to, oh, sorry. Let me say again, you may complain, it's so complicated, right? But it's something we cannot avoid, we have to see. So let, here is a capital P, n equal to, remember we at least we introduced the A0, it is the product. Then let we choose Bn is Cn square, Cn equal to D. Not only D divides n, D divides the P of n, this polynomial value. And here we have the mu of D. And another function, that's very indirect, sorry about that. Like this. And also, in order that this sigma, our question to prove it is positive, we are able to prove it, we need to make a constraint. Then what is capital X? Capital X equal to a power of, we are consider always the capital N goes to infinity. Now, what I did, why I could to prove this is positive, something like this, it is the power, it is this. Why we need this one? Because if the capital X is too large, we are unable to handle the arrow term. Sorry about that. We're unable to handle the arrow term. We're unable to prove the, in absolute value, the arrow term is smaller than the main term. So let me say, before my work, we may come here. People only can do something like this. Here, the 1/4 power of n. So in that case, if we choose something that I didn't say what is g of something anyway, like this. We take the capital X is the power of n, the exponent is less than 1/4. Then we are able to handle the arrow term, e is small. But the main term, we should be, of course, it should be positive. So still we are unable to it. Then, of course, people think about the possibility if this one. The major problem is that if x is equal to n, c is greater than 1/4 slightly, could be added, in my way, it's just add the reciprocal of maybe 500 or something like this, slightly larger. Then the main term m, we can prove it is green. But to prove that's the situation. So we say we just need to overcome one thing. We may make the c is a little bit larger than 1/4, even we say plus epsilon. But whenever c is a little bit larger, the main term is good. It is positive, what we need. But we are unable to handle the arrow term. Then what is my major contribution of I proved for a certain c larger than this, the arrow term is still small enough. This is my contribution. Here, I would like to say c equal to 1/4 bigger than 1/4. C equal to 1/4 originally, it was a consequence of the generalized Riemann hypothesis. But in 1964, two mathematicians, the former Soviet Union's Alexey Vinogradov and the Italian mathematician Enrico Bombieri, they proved that unconditionally, if C equal to 1/4, we are also able, just 1/4 minus epsilon, doesn't matter. We are able to control the arrow term. Their result is called the Vinogradov-Bombieri theorem. And that is a fierce metal result. But then after maybe more than 50 years, people try to break this boundary. 1/4 could make it a little larger. Actually, this is what I can say. I was the first person to break this. And also, here something like this, although we can't mention too much about the details. We know in mathematics there is another subject, the algebraic geometry, right? Algebraic geometry, also there are some Riemann hypothesis in algebraic geometry that corresponds to the variety over the finite fields. And the Riemann hypothesis originally was created to study the primes, the distribution of primes like these. But eventually we found that the original, the generalized Riemann hypothesis, even here in this way, even does not work. But the finite field Riemann hypothesis, that was proved in 1970s by Delin. I used one of his results. We borrow it from algebraic geometry to prove this one. In this direction, what I would like to say, this is just a beginning to the future. The beginning, we open the door to the future. There are lots of things we can do. So I just try to show something like this. Maybe it's still too complicated to something. So let me just stop here. I would like to answer your questions. Okay. Thank you. You have any question? Oh, you may ask.
Does anybody have any questions? Would you mind spending a little bit more time talking about how you went from down here on the bottom board, you went from, you defined this series A sub n, and then and you defined f of n, and then when you went up to question 3, you introduced this B sub n. Would you say a few more words on the relationship between the series A sub n and B sub n?
Oh, in the 3, we introduced something like this. We need to find the Bn. Then, as I mentioned, if we can prove such an inequality, that's enough, right? Whatever Bn, we only have a non-negative condition. But as I said, eventually is your result. If Bn here, this parameter is too large, we are unable, although we can get such a relation, we are unable to handle the error. So in order that we can handle the error, we require that this is not too large. We require that the C is less than 1/4. But the C less than 1/4, we cannot prove the main term is positive. But still, it does not work. My major breakthrough is that I prove for some C is greater than 1/4. Still, we can handle the error term. Then in that case, the main term is also very nice. We can prove it. Thank you.
Any more questions? So when you introduce these gaps, A0, A1, A2, it's kind of obvious congruence conditions on the gaps.
That's admissible condition.
Yeah, so there's some, is your instinct that those congruence conditions are enough? In other words, if you,
No,
there should be more information yet.
should be more information.
It's sort of like these Shimsel-Boniakowski, that the polynomials should represent many primes if there's no kind of congruence objection, but you think more would be needed for these.
Here I would like to mention the England young mathematician James Maynard, who just got the first medal in this question. He introduced a new form. Also, Bn is a square of something else, but the Cn is a different form. Is a more delicate, is a different form. Thus, he got some stronger result than me. But here, the question itself, can we break through the C is greater than this one? It's still my work. Okay, thank you.
You were proving your result. What made you gravitate to 70 million?
Oh, here, my apologize. What I can say, because at first I thought that this bound should be very large. I tried to just say it is C. There exists this constant C. But after finishing the paper, I find that the C could not be too large. Then I just this step. We have various steps. This step, we say the C should be greater than, say, 7 million. That way should be greater than 30 million or something. But whenever several conditions all conditions are satisfied, then that time I was also very tired. I didn't to check the possible best value, but I was sure that C equal the bound equal to 70 million is good enough. So I just put it. In my paper, the introduction, I said, to replace this one by a value as small as possible is an open problem. That will not be discussed in my paper.
So when you were a student, let's say undergraduate student, did you start to think about those mathematical problems? Also, do you have any general advice to our students?
Advice to your students. Yes, very early I started to think about these. And to my students, the young students, I just say one thing. If you really love mathematics, do not easily give up. You just keep going consistently and try to find some new idea, in particular to find something new connection between something, the various part of mathematics, maybe that looks totally different, but there maybe the major part to make the progress in math is to find the connections between something these, and do not just trust other people tell you this is impossible, something like this. Actually, let me tell this one. It was before my work, 3 mathematicians had been working for this problem for more than 20 years, and eventually it is just blocked here. Can we find a way to prove that even C is greater than 1/4? Oh, the final conjecture is C. As long as C equal to 1/2 or 1/2 minus epsilon, it is also true, but still we are unable to do. I just say C is greater a little bit. Then in 2008, there's the American Institute of Mathematics organized a workshop. So there is many experts came to discuss for 1 week. Eventually, this workshop gave a conclusion. In current situation, we are unable to break this. But at that time, I didn't know this workshop. So if I knew this, should I give up? So keep going. Try to do not think the people before you are very smart. You cannot be as good as them. Yeah, I could be much better than them. Okay, thank you.
Any more questions? You can ask Professor Tom anything you like. It doesn't have to be mathematics. Yep. Go ahead. I can't see you here. Yeah.
What was your favorite level of mathematics?
We can say still number theory. And let me say, the analytical number theory could be not very popular. The reason should be it's not important. We say the Riemann hypothesis, Goldbach conjecture or something, everything, not everything, but lots of famous things belong to the analytical number theory. But also what I like to say, this one is very challenging. So it's difficult to make the progress in this one. But in that case, for example, let me show it's elementary number theory. We know the prime number theory, right? And we, at the very beginning, that was the first proof by Adama and Zhang, some two mathematicians. They went along the rule, the door just opened by Riemann, using the Riemann zeta function and the analytical tools to prove the prime number theory. Then the English mathematician Hardy in 1921 gave a prediction. The prime number theory can never be proved using the elementary method. But in 1949, Serberger and Eidish, now there are some arguments say the major discoveries from Serberger give a elementary proof of the prime number theory. I say it is elementary now is that it does not use anything about the Riemann zeta function, even though the complex analysis, but it use a little bit of the properties of like the e raised to x, natural log of x, something. So it is elementary. So in analytical number theory, lots of things are possible if you can find a correct way to do it.
Yes, yes, right.
Work in progress in the field that you're particularly excited about?
What? Excuse me?
It's something now in progress that is very exciting to you. Some general work that you think is very interesting.
In analytical number theory, there should be some, but let me say, just a couple of days ago, I made just an informal announcement in the Alumni Association of Peking University. I mentioned I got some very good result. Now online is a lot of news, but otherwise, I don't know, maybe something, may not got something very good. Okay.
Hey, yes.
There's a question from my friend. I don't know what that is, but I'm just gonna read this out. Is it possible to use a GYC method to study a common number? Recently, a young man proved that when the positive integer is sufficiently large, there is always a common number between n and 2n.
It is possible. It is very possible, and maybe it is now. It is not only possible. It is. It become the truth, right? I know this one. You say the GPY, yeah, goldstone pins and yielding before my work.
One last question. Does anybody have one last question?
How did you study for math in undergrad?
How did I study? Because I don't know, because when I was maybe 8 or 9 years old or 10 years old, I read some books just introducing something, a lot of math problem like Kullbacher conjecture, the Fermat's last theorem. I learned at that time. It was not difficult when I learned these things.
Hold on, we have one more surprise for Professor Tom.
Want to give you these on behalf of the students here at Queen's College.
Okay, thank you. Thank you so much.